Again, our objectives here, we're going to essentially define some of the basic concepts when we talk about electric circuits. And again, the class is Principles of Electric Circuits 1 and the lab. So let's look at electrical safety. Again, safety is the most important principle that a student should learn before working in a laboratory. Okay? It is important to identify conditions that can become a hazard in electronics laboratory and to be familiar with the laboratory safety rules and eliminate such hazards. And we have two examples of hazards. Power supplies can be a shock hazard if they are not turned off before working on a circuit. So before you work on a circuit, we need to ensure that the power is out. Okay? And we have another hazard. Soldering irons could be a source of burn hazard and can also damage equipment. Can you put up your cell phone, please? Yes, sir. Okay. Current through the body is electrical shock. Again, before we continue with our safety, we need to know what this current, all right? How does current go through the body? And so we're going to move to, let's turn to page 3, and we're going to come back to electrical shock. Page 3, on the circuit fundamentals. So anytime we talk about electricity or a circuit, we want to look at the foundational principle is that of electric charge. All right, and we'll start by defining. I'll start by drawing a hydrogen atom. So again, keep in mind we're defining current. What is current, right? Okay, so here we have a hydrogen atom. What are the parts of this hydrogen atom? Yeah. Electrons. Someone else?
And proton.
Proton. Okay, and we have neutrons. All right. What kind of charge does the electron have?
Negative.
Okay, negative charge. And the proton?
Positive.
Okay, positive. And the neutron?
Neutral.
No charge. All right. What is the net charge of any atom? What is the net charge? And when we say net charge, we are asking, is it neutral? Is it positive? Is it negative? This atom here, is it? Does it have a net charge? If it's neutral, then the net charge is 0. So what is the net charge of this atom? 0. All right, because we have one positive and we have one negative, and these charges are almost like they're canceling each other, right? Okay. Also, we have also keep in mind that this electron is being kept around the atom. In other words, this is circling it's circling the nucleus because of the force of attraction. Okay, and what is the force of attraction? If you look at figure 1, we have just 2 charges, and we can, the same rules apply to magnetic poles. 2 like poles are going to do what? Repel. Okay, so 2 like poles are going to repel, right? And 2 unlike poles are going to do what? Going to attract. So do we have any attraction here? Yes. So we have attraction between the electron and the proton, and this attraction or this force is what is keeping the electron circling the atom. So it's keeping the electron within the boundaries of the atom. Right? What if this electron gains some energy? Could be through heat or through some other means. What if it gains some energy and it decides I'm leaving this atom, I can break free. Alright, what will happen? What do we call this if it loses one electron? Ion. Yes, we call it a hydrogen ion. Correct? So I'll just draw. So here we have only one proton. Does this ion have a net charge? Yes? Speak up. Does it have a net charge? What is the net charge? Okay, so we can write here. What is the net charge is? +1. Okay, because there is no negative there to offset that positive. Okay, likewise, if this electron that left goes and it joins it joins another hydrogen atom. So now we have 2 electrons here. What will be the net charge here?
Negative 1.
Okay, correct. The net charge is -1 because we have an extra electron. And we know that the electron will have a negative charge. Right? So again, the 2 basic rules we said: like charges are going to repel, and unlike charges are going to attract. We're going to have a force. And of course, if we held 2 magnets of opposite polarity, we can feel the force of attraction. They want to come together, right? Okay, so that charge that the electron has is actually measured in a unit called the coulomb. Okay, so we say, yes, we know electrons have charge. They have a negative charge. The question is, how much charge do they have? Okay, if you look in your handout, you see that each electron has a negative 1.602 times 10 to the minus 19 coulombs. Okay, so the unit of charge is the coulomb. And the charge that an electron has is a very, very, very small amount of charge. Okay, it's a very small fraction of 1 coulomb. Likewise, so if we wanted to know, well, how many electrons does it take to make 1 coulomb of charge? Each electron has charge. It takes 6.24 times 10 to the 18 electrons so we can have 1 coulomb of charge. All right. So just anytime we talk about current, we will talk about electrons moving and electrons flowing, and we talk about the flow of charge. If the electron has charge, if the electron is moving, then the charge is moving, right? Okay. So keep that in mind. So before we continue and we get the formula for charge, let me just draw a simple circuit with a battery. Now, take a definition for a circuit. You can take it down. A circuit is the interconnection of electrical components. An interconnection of electrical components. In other words, there is a closed path. So it's an interconnection of electrical components. I'm going to put the basic circuit on the board. Just going to use a battery. Okay, how many of us have used AA batteries? Yes. Okay, we have a battery right there. Okay. So when the circuit is closed, we have electrons. What happens here? Electrons are going to leave this negative terminal, right? They are going to be repelled. So we said like forces are going to repel, right? So electrons are going to leave this negative terminal. They're going to be repelled from this negative terminal, and they're going to travel all the way here. They're going to travel. They're going to go through the light bulb. And when they go through the light bulb, right, the energy that they came from the battery with, this energy is going to be converted from electric energy now into light energy, right? And so these same electrons, having lost the energy, they are going to go now to the positive terminal. And again, there is a force of attraction at the positive terminal. So the positive terminal is attracting them, right? And this terminal is repelling them. Again, keep in mind that a battery is a form of potential energy, right? So I'll just make a few notes here. So again, this is the form of potential energy. And it's in a chemical form. In other words, with the battery, the way it works is that we have a reaction taking place inside the battery, and that reaction causes it causes the production of electrons, and and not just any reaction, but these electrons have a higher energy. Okay. Now, when this reaction happens, right, these electrons are produced and they have a high energy level. They come from this battery with a high energy. And I'll put just 3 dots here to show that they have a high energy. And when they pass through the light bulb, they perform work. And that work, what we're saying is that this electric energy is going to be converted into light energy. Alright? And of course, the light energy is radiated from the light bulb. And so here we have the electrons, and they're at a lower energy level. So again, here they're going to be at a high energy level. Here they're going to be at a low energy level, and they now attracted to the positive terminal in the battery. And of course, that continues the reaction until the fuel for the reaction is no longer there. Okay, and we see the battery is flat at that point. Okay, so first thing we want to define is current. So the definition says electric current is a measure of the rate flow of electric charge, or the measured charge that flows in 1 second, and this can be represented using the equation I is equal to Q over T. Again, each electron contains a percent of charge, correct? So current is the measure of how much charge flows in 1 second. So just imagine that we have a valve here. We have a valve, and we are measuring the flow of charge. All right? Think of water. If we have water flowing through a pipe, we are measuring how much water flows in 1 second. In fact, this is how we get our flow rate for water. We have no drinking or eating in the lab. That's one of our safety rules that we'll come to. Okay, if you want to drink, please step outside. Again, so we actually measure flow in gallons per minute. So if you want to buy a pump, one of the specifications on the pump would be what is the flow rate. Okay, especially if those of you who use pressure washers, right? You want to know how many gallons per minute can this pump put out. That measure of flow of charge is actually what we call current. So normally we would have an ammeter here. I just draw A, and what will happen is that the current would flow through the ammeter, and then the ammeter will be able to measure the charge per second and be able to output that as current. So again, the equation for current, and we use I to represent current, and we said in class the unit for current is the ampere. I is equal to Q. Okay, hold on. Is it Q or C? Okay, Q over T, where Q is charge in coulombs and T is time in seconds. Okay, so this is how we get current. We know how many coulombs of charge are flowing in 1 second. So here's a small problem just to apply this. What if we had our ammeter there, and we knew that we had 2 coulombs of charge? We knew that we had 2 coulombs of charge flowing, and we were measuring for a period of 3 seconds. What would the current be? 2 coulombs of charge, and we knew that we measured for 3 seconds. 2 over 3 coulombs. Okay, so it's going to be 2 over 3 amperes. Yes, 2 over 3 amperes of current. Okay, let's look at another example. What if we had 1 coulomb of charge flow in 2 seconds? Okay, 0.5 amperes. 0.5 amperes. Okay, so again, current is the rate flow of charge. We're actually measuring how much charge is flowing in 1 second. All right. Since we're here, we can also talk about fuses. How many of us are familiar with fuses? How many of us have changed a fuse before? Yes. A fuse is what kind of device? What kind of device is a fuse? What do you use your fuse for?
Fuse to protect.
Protect. Correct. A fuse is a protection device. Just like we have some breakers. You see some breakers at the top there? These are also protection devices. Okay, so okay, this is the symbol for a fuse. I'm going to put the symbol for the fuse here. You can take it down. Okay, how does a fuse work? So a fuse is a protection device, and a fuse uses current, not voltage. It uses current to protect a circuit. The fuse is, what it does, it has an element that is rated for a certain amount of current. Okay, so the element inside of the fuse, and when we say element, we're talking about the conductor inside of a fuse. Okay, the conductor inside of a fuse is rated for a certain current, amount of current. if more current than if more current is flowing through the conductor than it is rated for, then the conductor will heat up and eventually it's going to melt. And when it melts, it breaks the path for current to flow. That's why you see normally the fuses have glass around them. If you've seen those that are clear, and there's a thin wire inside. When that melts, then the path for current to flow is broken. Okay, so in other words, current is not going to flow through the circuit. Right? Okay, so we understand what current is. The flow of charge, coulombs of charge per second. Alright? Okay, so while we are here, we can talk about conductors and insulators. What is the difference between the two of them? All right, what do we normally use to conduct? So we said electrons, all right, the electrons have charge, and the electrons are going to be pushed from the battery, and they're going to flow through our device, and they're going to perform work. So now we can talk about work and different types of energy. What are the rules that we know concerning energy? Let's define energy, right? So we talked about energy here. We said that these electrons have energy, and the energy is converted into what kind of energy here? Light energy, right? Okay, so let's talk about energy. What is the rules that you know concerning energy? Anyone? Have you heard that energy cannot be created or destroyed? How many of us have heard this? Okay, all right. So if it cannot be created or destroyed, what do we do with it? Say again? Manipulate. Use another word. That's a nice word, but you should use another one. Change. Convert. Someone said convert. That's very good. So change is also good. So energy cannot be. So I'll put two rules here. Cannot be created or destroyed. Okay, but can be converted into other forms. All right. Okay, we have that. So let's list some of the forms of energy that we know. Forms of energy. Okay, we have heat or thermal. Anyone else?
Kinetic.
Correct. Kinetic. Potential. We have kinetic. Anyone else? Light. Anyone else? Other forms of energy. How about electric energy? Correct. Electric energy. Anyone else? Heat, potential, and of course we can go with, we can say nuclear, but it's going to be thermal as used. Okay, so these are some forms of energy. And on this here we have electric energy. Alright? So, cannot be created or destroyed, but can be converted from one form to the next. Now, if we look at our electrical system that we have, energy in the form of heat. Alright, so we have potential energy. Where we have some hydrocarbons, they are burnt, right? And because of the burning, they produce heat, they produce thermal energy. And that thermal energy, most of the time, is used to produce kinetic energy, where it goes to turn some generators, right? Okay? And then these generators produce electric energy. And this electric energy is, moves from one area to the next, okay? It's transferred from one area to the next. All right. What do we use to transfer electric energy? Someone said circuits. We use conductors. Okay, so that's why I want to talk about wires and conductors. So we use conductors. So conductors, you can say transmit. Okay, so conductors transmit electric energy. So we use conductors to move energy from one area to the next. We move energy from the generation plant to our homes to the lab right here. Okay, so what are some of the properties of conductors? I wanted us to know that. What are some of the properties of conductors? We drew a wire right here, right? And we said that this is a good conductor because we show that our electrons are moving through that wire. What are some of the properties of conductors? Go ahead.
They can be made of metal.
Okay, most times they're metallic. I'm looking for something else. So I'll just put metallic here. Properties of conductors. Now think, the opposite of a conductor would be what? Insulator, right? And what are some of the properties of insulators?
Don't transmit electric energy.
Correct. They oppose the flow of electricity, right? So put here, oppose the flow of electricity or electric energy. Alright? So again, we said conductors are normally metallic. So what you want to put for conductors is that they allow electrons to flow through them very easily. Alright? For conductors, they allow electrons to flow through them very easily. And we said metals are very good examples. So they allow electrons. And why electrons? Because electrons have the charge. So if electrons are flowing through them, again, guess what? Charge is moving and then we have some current, right? So they allow electrons to flow through them easily. Okay? Now, of course, the opposite is true for insulators. Again, if we have a live wire here, all right, and we don't want to get shocked, but we want to hold the wire, we're going to put a glove on, right? And that glove most times is rubber or is leather, all right? Something that most likely is dry, okay? So that we can prevent these electrons from coming into our bodies. Because again, we're talking about safety, right? So they oppose the flow of electricity or they oppose the flow of electrons flowing through them. Okay? Now here we have a piece of wire. Of course, some of them, I'll just list some materials that we use for conductors. Most times they're going to be copper or silver or aluminum. Right? Iron you will get, but iron has very high resistance. And we're going to talk about resistance in a second. So again, the most popular materials we use for conductors, like all these wires you see here, inside of them, most times we have copper. Okay, that's the element copper. Or we have aluminum. Okay, or we're going to have, if you want better conductors, they'll be more expensive. Silver and gold are very good conductors. Even platinum and lots of other materials. But the most popular one we use is copper. Alright? Again, for insulators, we use rubber, we use leather, we use mica, a number of other materials as well. Okay. What property does water have? Is water a good conductor, a good insulator? Conductor. Okay, that's why we don't want to drink any water in the lab. We don't want to expose ourselves to getting shocked. And we'll see that as part of our rules. So after current, we want to look at the second thing we have here is voltage, right? We're still on page 3. All right. Voltage is the driving force that causes the flow of electrons. So what causes the electrons to flow? We said they are being repelled, right? Voltage is the driving force that causes electrons to flow. And of course we say if electrons are flowing, then what else is flowing? Charge is flowing, right? Because electrons have charge. All right? The voltage or electrical potential between 2 points in an electric circuit is defined as the energy produced per coulomb of charge while moving between 2 points. A common source of potential voltage is a chemical battery. One electrode is more negative, and because of the chemical reaction which produces free electrons, these electrons are repelled from the negative terminal and travel through the conductor, which is a copper wire, to the positive terminal of the battery. The work produced for every coulomb of charge is voltage. So again, voltage is the work produced for every coulomb of charge that flows. So for every coulomb that flows, the work that is produced is actually our voltage. Okay, so I'll put down a formula for voltage. Let me move the hydrogen over here. So voltage is the work produced for every coulomb of charge that flows. Okay? So in our circuit, right? If we knew that, say we knew that we had, and we find in V, we had 2 coulombs of charge, 2C, right? And we produced 10 joules. 10 joules. In other words, 10 joules of energy were produced, right? Okay? Then we can find our voltage. What will our voltage be? 5. And what is the unit for voltage? Okay, the unit for voltage will be the volt. 5V or 5 volts. Okay, so again, you can go down to the basic definition for voltage. If we have a circuit where we have, for every 1 coulomb of charge that flows, we have 1 joule of energy being produced, then we'll say that we have 1 volt present. And again, remember that the voltage is what is driving the electrons. Okay, the voltage is causing them to move. Okay. Also, want to keep in mind that we can't have voltage without current. An electric potential of 1 volt between 2 points, again, voltage is always between 2 points, will produce 1 joule while 1 coulomb of charge flows. Is moved between the 2 points. Voltage is measured across the terminals of a circuit element. When voltage is increased, current will also increase. And the reverse is true. Voltage, however, can exist without current. Again, current is the flow of charge in 1 second. Now let's look at the illustration of a water tank. Say we have a tank of water, like the, right? How do you call this? Okay, we have this guy up here, and it has water inside. Correct? Okay, and we have a tap coming down here. Okay, this is a source of potential energy. Why? Because gravity is acting on that water, and it's essentially weighing it down. So if we open our pipe here, we're going to get a lot of pressure coming out, right? So think of the pressure as the voltage. Okay, between the tank and ground, this is going to be the 2 points. So we have a voltage existing. When we open the tap, what happens? We have flow of water, right? Anytime we close the circuit, right? Anytime we close the circuit, we have current flowing. We have water flowing. Okay, that will be our current. But if we every time we open it, we have water flowing. When we close it, we have no current, but we still have voltage because we still have the potential to do work. So voltage is almost like it's a potential. We call it the potential difference. It's the potential to do work for every coulomb of charge that flows. Okay, let's talk about resistance. All right. Talk about resistance. Again, we talk about current. We said current is the flow of electrons through a material. Now, different materials have different properties. Some materials allow current to flow through them very easily for the conductor, right? And some of them, they oppose the flow of current through them. Okay? This we call them insulated. They are pure resistors. But then there are some materials that we manufacture, and we manufacture them to have a certain resistance. So yes, current will flow through them, but we want them to have some resistance as well. We call these resistors. All right. Again, keep in mind, materials with a low resistance, okay, again resistance, let's think of it. Materials with a low resistance, they act like conductors, okay? They allow a lot of current to flow through them. And materials with a high resistance, they allow a small amount of current. So in other words, we can limit the amount of current flowing from material by using a particular value of resistor. If we have a large resistance, then we only allow a small amount of current to flow. If we have a small resistance, and we can go as small as 1 ohm, and we see that the unit for resistance is the ohm. If we have a small resistor, we allow a large current to flow. And again, that current is going to be determined by the voltage. Right? And of course, we're going to see that we will use a law called Ohm's law to relate voltage, current, and resistance. So today you're going to see a resistor. We are going to measure the resistance of that resistor. We are going to actually measure the current that is flowing through that resistor when we apply 5 volts to it. Okay, so now we talk about current, voltage, and resistance, right? Let's go back to our electrical safety and we'll talk about electrical shock. We are on page 2. Okay, current through the body is electrical shock. If the electrons leave the circuit and they jump onto your body and they enter your body at one point and they leave your body at another point, then we call that electrical shock. Okay, now most of us have been shocked in our lives. How many persons have been shocked in here? Yes. Okay. Was it a bad shock or was it just a small shock? Okay, some bad, some small. Okay. The severity of the shock is determined by many factors, and one of the important factors is the amount of resistance at the point where the current enters. Because some parts of your body, you know, they have more resistance than others. For example, there are some places on your body where your skin is very soft. Now your hands, you have some tough skin there. But probably behind your ears or somewhere else, your skin is very, very soft. Sometimes it's moist. And these will be points of low resistance for the current to go through. So let's look at the second paragraph. It says, when a part of one's body comes into contact with a voltage and another part comes into contact with another voltage or ground, such as a metal chassis, there will be a current through one's body from one point to the other. The severity of electrical shock depends on the amount of voltage and the path the current takes through your body. The amount of current is dependent on the resistance of the human body, which in turn is dependent on a number of factors, such as your mass, skin moisture, etc. And again, we're going to look at the lab rules. So current may come through you, but it passes a different route to exit. It may exit, if your arm is touching something, it may exit through your arm. If your legs on the floor, it may pass to the floor. Okay, so the degree of shock you experience depends on the path that the current takes. Okay, and also it depends on the resistance. If there is a large resistance, a small current will go. If you have a small resistance, a large current is going to pass through your body, and you can even be killed. Okay. Please read and be familiar with the lab rules. We're going to do that in a second. Before we go to the lab rules, I want to talk about short circuit devices. So what is a short circuit? How many of us have heard of short circuit before? Short circuit, what is a short circuit?
When too much power goes into something and it can't hold the power.
Okay, so it says too much power. So we'll talk about power later. Power essentially is how fast anything uses energy. So if we have 1,000 joules of energy, and even if you and we have two components, and one uses the 1,000 joules in 2 seconds, and the other one uses the 1,000 joules in 5 hours, then the one obviously that uses faster will be using more power. Okay, so power is the rate at which we use energy. So let's talk about a short circuit before we talk about short circuit devices. Okay, so when we talk about a short, normally we say that we have a conductor that is bypassing a load. Okay, so have a look at this circuit here. So one of the devices that we talked about is the fuse. Actually, a fuse is a short circuit protection device. Why is it a device? If we have too much current, what will happen to the fuse? It's going to stop, it's going to break the circuit, right? Okay, say we have a battery, and this is a symbol for a battery. So we don't normally draw a battery when we draw our circuits. We use this symbol for a battery, where this represents the positive, the long side, and this side represents the negative. So this here is our load, right? It represents our load, and our load can be anything. It could be a light bulb, it could be a fan, it could be a motor, it could be a heater. Anything we use, anything that is converting our electrical energy to a different source is going to be our load, right? Okay. Since we talked here and before, and come back to efficiency. So anything that converts our energy into a different source, like it takes our electrical energy and convert it to another form is our load. One thing I also have to tell you, so I have a resistor here. So this is the symbol for a resistor. And again, we said the resistor is restricting the flow of current. Now, the way the resistor works is that it actually converts that electrical energy into heat. So most of the resistors, if you touch them, they're going to be warm because they are actually converting electrical energy into heat. Okay, so they also act as a load as well in your system. So we have this here representing a load. Okay, so again, we said current is going to leave here and it's going to some energy is going to be converted into heat here, all right? So only a limited amount of current will flow through here, all right? If we have a wire that comes from here and it goes across our load, we call this a short. Okay? What will happen as a result of this wire here? What do we think will happen? So remember, we had a resistor right here that resisted the flow of current, all right? If we have a wire here that is shorting out our load, where do you think that the current will go? The current is going to pass through the path of least resistance. So it's going to go through this wire. And again, we said the wire, the conductor, has a very, very small resistance. As a result, a very large current will flow through it. Okay? This is what we talk about when we say we have a short. When we have a short, the circuit is drawing too much current. All right? The current is very large. That is why we need a device like a fuse or circuit breaker to detect that large current and to be able to break the circuit. The fuse is going to the element is going to melt and it will stop current from flowing. Alright? Or if you have a circuit breaker, it's going to open the circuit and stop current from flowing. If we don't have a closed path, we will not have current. Okay, we will have voltage. We'll have a voltage here between these 2 points, but we won't have any current. Alright. So again, it's important to know the function of these devices and not to tamper with them. Before we move on to our lab safety rules, I wanted us to talk about efficiency. So we said energy cannot be created or destroyed, and we have different forms. It's just converted into other forms. We said we use electric energy. Most times we use electric energy is used in other forms. For example, we have this light bulb here. This light bulb is using electric energy. So we took the energy from wherever it's generated and we transmitted it using what? Wires, right? And we took it into this room, right? And now we are converting it from electric energy into light energy, right? So again, the majority of devices we have, that's what they do. They actually convert energy from one form to the next so we can use it. Think of your home, the water heater, same thing. It converts that electric energy into what kind of energy? Heat, thermal energy, so you can use. All right. So one thing we need to talk about when we talk about the using energy is efficiency. Does anyone know what efficiency is? Efficiency, I mean, we use it as an adjective to describe ourselves in our resume. I'm very efficient. Okay, so tell me, what is efficiency? Okay, in the sense of energy, efficiency is how well a device converts energy. So we said we use all these different devices to convert electrical energy into other forms of energy. So efficiency tells us how well a device converts energy. So it's a measure of energy conversion. What do I mean? Okay, this light bulb, this light bulb, say it takes 1,000 joules of energy. So we calculate the efficiency. This light bulb takes 1,000 joules of energy. So the energy in okay, so we have energy in over energy out. That will be efficiency. Okay, so the in is the total energy in, and the out is going to be our desired energy out. And let's use the example of this light bulb here. So this light bulb takes in 1,000 joules of electric energy. Alright, so this is the total energy going in. So it has 1,000 joules of electric energy. Take out the, it should be out over in. Sorry about that. So energy out over energy in. So it takes 1,000 joules of electrical energy. And when we take our light meter, right, and we're measuring, we want to know how many joules of energy is this light based on the light intensity, right? What is the energy being put out by this light? We measure and we find out most times it's not 100%, because most times you never get devices that are 100% efficient. Okay, probably we get this is putting out 200 joules of light energy. Okay, using this, we can calculate, we can multiply this by 100, we can calculate the percentage efficiency of this light bulb. What would it be? Where is that?
Oh, you just erased that.
Yeah, this is going to be the desired energy out, and this is the total energy in.
Where do you get times 100 from?
Okay, this is just to get percentage. Okay, so again, efficiency tells us how much of the energy we want is actually being converted. So we put in 1,000 joules of energy in this light bulb, and we're measuring the light energy coming out, and we're only getting 200 joules. So we can use that to calculate the efficiency of the light bulb. It's going to be 200 over 1,000. So this is going to be 20% efficient, right? Which is not very good, right? Okay, and again, we can look at a number of devices and we can calculate the efficiency based on the amount of energy they use and based on the needed energy or desired energy that they output. Okay, let's move on to the next section, which is how do you connect an electrical circuit? Page number 4, constructing electrical circuits.
That's why I'm letting you try to look at the time.
Okay, constructing electrical circuits. Are you guys tired? I see some people are standing. Are you standing? Okay. Okay, so again, listen. We want to know how to construct electrical circuits. Okay. If you notice on our paper here, if you turn to page 5, we have a simple circuit that we're going to do. I'm just going to draw this one out and we're going to talk about how we construct it. So I have a battery, and I have a light source, which is the LED, and we have one resistor. Okay, so we have 3 components here. This is a component here, a resistor, right? Okay, this is a component. I'm just going to circle it, and this is a component here. This is the LED, the light source. Okay.
The symbol for it or something?
This is the symbol for the LED, right? The symbol, I just circled it. The circle is not in the symbol. And then this is the battery. Now, most times in the lab, we don't use batteries, we use power supplies. And the power supply is in front of you. This is what it looks like. Okay, this is the power supply. Okay, it has positive and negative output terminal. All right. So again, if we know that this is positive and negative. Okay, so how do we form a circuit? We need to make connections between components. All right, we need to connect our power supply to this leg of this component, or we call it the lead, and we need to connect this leg of this component to this leg of this component, correct? Okay, and we need to connect this leg of this component back to this leg of this component. So how do you make connections? We use what is called a breadboard. Yes, it's called a breadboard. Okay, if you notice, and I have an example right here, I can show you. So this is the breadboard that we're going to be using, and we use it to make connections. All right. If you notice on your paper on page 4, we have an example of a smaller breadboard. Okay, and this smaller one, we're just showing that all of these rows are connected. So if you wanted to connect 2 legs of 2 components, we need to put them in the same row. Same thing happens here. If I have 2 components, and I'm going to take the 2 components we will be using for the lab, just a resistor and a LED. Okay, so this is the LED, You can't see it, it's a small light bulb. Alright? If I wanted to connect this leg here, the short leg, which is the negative leg, if I wanted to connect this short leg, so if you look at your circuit here, if I wanted to connect this negative leg to my resistor, so again this has 2 legs, and this one has how many? 2, right? So according to my circuit, I have a resistor right here, correct? And I have my LED right there, right here. And I want to connect them. To connect them, this is like a physical connection. But what we use in the lab, we use the breadboard. So if I want to connect these 2, I'm just going to put them in the same row on the breadboard, because this is just like a connector. So now the 2 of these, we have this connection done right here. Okay? Similarly, if I want to connect this to my power supply negative to this one, I need to put this one in one of these channels. Okay. All right. Okay, so if you look at our circuit here, we have our power supply positive. Now, if this is coming from my power supply, this is the positive from my power supply, and I want to connect it to the leg of the LED. I simply have to put it in the same row with it, because then it's going to be connected to it, right? Because we have the material behind this is conductive, right? So it's going to make a connection. Likewise, and again, this does not go to a battery, but this represents our power supply. So this positive goes to our power supply, correct? Now, we can see that the negative of our power supply, what is it connected to? It's connected to the other leg of the resistor, alright? So again, here's my resistor. So one leg is connected to the LED, and we have that right here. And the other leg is connected to the negative of the power supply. And so we can connect that right here. Right here. Alright? And then I'm going to connect this to my power supply. I'm going to turn my power on, and you're going to see that it's going to light up, right? Okay, so this is the small section here. The next section, very short as well, is electrical measurements. Okay, we're familiar with current, voltage, and resistance. Well, how do we measure them? Alright, and of course, we need the diagram to show how we measure these. Okay, before we move on, since we're using the LED today, if you notice at the top here, we have the symbol for the LED given to us, and it tells us that the LED only works in one direction. Alright, so you have a light bulb, but it only works in one direction. In other words, one of the legs is positive and one of the legs is negative. And as you notice here, one leg is longer than the other. So the long leg is the what? Positive, correct. So long leg is positive, short leg is negative. Alright, so let's talk about our electrical measurements. So again, before we use a number of different meters to measure these quantities. Like we had an ammeter to measure current in amps, right? We had a voltmeter to measure voltage in volts, and we had an ohm meter to measure resistance, because the unit for resistance is the ohm. Alright? But today we're using digital multimeters, and we just have to change the functions and probably change the probes to be able to measure current, voltage, and resistance. Okay? So with this meter here, notice that the red lead is in the volt and ohm port, while the black one is in the common port. Okay? So to measure voltage, I need to turn this one to DC volts. Okay? And to measure resistance, I need to turn it to resistance, and then I will measure resistance. So how do you measure voltage? We always measure voltage across the component, because voltage is the potential difference between 2 points. So voltage is always measured across a component. So for example, if we were to measure voltage across the resistor here, and the lab actually says measure the voltage across the resistor, how do we do that? We take one lead of our meter and we will put it right here. So in this case on the breadboard, we're going to put it in the hole so it can connect with that part of the circuit. So it's going to be right here. So this represents the meter, voltmeter. Well, this is the positive lead and the negative lead. And if we are told to measure the voltage across our LED, we also will do that here. What about if we are told to measure the voltage across our power supply or from the power supply? Same thing. One lead of the voltmeter is going to be there, and the other lead is going to be here, right? Correct. Okay. The next thing we want to talk about is measuring resistance. Okay? To measure resistance, we need to make sure that the circuit is off, that the circuit is not powered at all. Right? And we take the resistor by itself. Okay? So we put the resistor in a section by itself, and then we measure the resistance. And we can do that first. Right? We ensure that our meter is set to the omega symbol to measure resistance in ohms. And we will put our leads across here, and we'll measure the resistance of the resistor. Alright? Now, the last thing we want to talk about is measuring current. Okay? To measure current, we said the electrons must flow through the meter, right? So that we can calculate the amount of coulombs per second. So current, essentially, we need to set our meter to the milliamp setting, and we also need to change the probes because we have some special circuitry to measure current. Right? So if you notice at the bottom of the meter, there is a port for milliamps. And again, we know a milli is 1/1000th of an amp. Alright? So we need to move this red probe into the section that says milli. That's to measure current. Okay, and what we do next, we need to break. So the next thing we're going to do, we're going to interrupt the circuit, and we're going to allow the meter to serve as a jumper. For example, here, I can decide to interrupt the circuit right here. Right here. And allow the meter to serve as a jumper. So my meter is going to serve as a jumper right here. And why is that necessary? Because I want the electrons to flow through my meter. Okay, current is never across a component. Current is always just in series with the circuit. We just want to know what is flowing through the circuit. Whereas voltage is across a component. Resistance is across a component. Current is never across a component. Okay, we don't want to do that. We will damage the meter. As a result of doing that, almost all the meters are damaged. And when it comes to your current measurement, I will help you do your current measurement because this one works. I don't know about the others. All right, but you can still try. Okay, so with that said, we want to move to the procedure. Okay, and we are going to begin at number. We are going to begin with number 4. Number 4. Okay, hold on. Number 3, sorry. Number 1 and 2, you need to do for your lab report. Okay, we are going to begin with number 3. Now, before you start measuring anything, what you want to do, you want to construct your circuit as shown. Okay, and then you're going to go ahead and do your measurements. Okay, so I'm going to give a demo in the front here. So also I want you to work in groups for this lab. So if you can work in groups of 2s, that would be nice. Okay, work in groups of 2s. Each group is going to have their own power supply and their own components to build a circuit, and they're going to have their own meter as well. Okay, so please come to the front. I'm going to give a short demo. Alright. Again, this is very simple. You guys should be done in no time. Right? So the first thing we want to do, we want to take our resistor, and each team will get a resistor and a LED, and we're going to measure the resistance of that resistor. So to do this, our meter needs to be on ohms, and this port needs to be in the ohms port as well. And then we just put it across the components. The polarity does not matter. Here, and the resistance is going to appear on the screen. So here, the resistance here is 326.4 ohms. Now, if you notice in your lab, we have a data section here. We have resistance of the resistor. Now, we don't have a 470 ohm resistor. This is showing 326.6. It's actually a 330. Now, there's a way you can find the resistance of the resistor by looking at the colors. We'll talk about that later. So I'm going to start here, 326.5. I'm going to take another measurement. 326.5. I'm going to take a third one. 326.6. Second thing I want you to do is to now construct a circuit. Now again, just like we have it on the board, we have the LED and the long leg is the positive. So the long leg is going to be connected to the supply. So I'll start with the positive. So again, we're using this fixed 5 volts here. So we push this yellow in this port here. So this is our positive, our supply, and we want the positive. I'm going to just put it right here. And the positive is connected to it's connected to the positive of the LED. Now the long leg is the positive of the LED. And the negative, the short leg, the negative leg is connected to the resistor. So I need to put it in the same connection here with the resistor to make a connection. Now the circuit does not have to look like mine. It doesn't have to look like this. It can be in a straight line as long as you have an interconnection. Alright? Okay, so I have this here, and then the next thing I know is that the negative is connected to the negative of the power supply is connected to the other side or the other leg of the resistor, which is right here. So I can put this here, right here. Okay. Now if I turn my power on, I should have a light here. Alright? Okay, next step the lab says is we should measure the power supply voltage, and then we're going to measure the voltage across the LED and the voltage across the resistor. These are very easy. I go to DC volts here, and I want to measure the voltage across the resistor. So I put this across the resistor here, and I take the voltage 2.971 across the resistor, and I do 3 such measurements. Okay, this one is going to be 2.990. At the end, we're going to get the average of these 3 readings. Likewise, I need to get the voltage across the LED as well. Okay, 1.996. 1.996. What you notice is that these two voltages are going to add up to our power supply voltage. Alright, now to get the power supply voltage, I'll move. So these are the 2 inputs for the power supply. I'm going to move this right here, and I have the power supply voltage as 4.98 volts. Okay, and these are all the measurements that we need. The last one we need is the current. Like I said, I'm going to help you with the current. So like I said, with the current, we actually interrupt the circuit. So let me measure current here so you can see. So again, this is the milliamp port, and we have the milliamp setting here for current. And we actually want to interrupt the circuit and make this a jumper. So to do that, I'm going to put this right here, and I'm going to use this as a jumper to go from here to here. I'm going to turn this on. Alright, and now I get the current being positive, the current flowing through the circuit as 9.07 milliamps. Okay, thousands of an ampere. Okay, so this is what you have to do. Let me give you your components, and you can be on your way to your tables.